So this video is going to be relatively short, I hope, and it covers projectile motion. Now, projectile motion is an important half of the course, in the first half of the course particularly, but you use it throughout, and you use the idea looking at things from essentially for a significant part of the course. You look at this. And I'm just going to try and define the basic motion or equations for the projectile motion and start to reinforce this idea that eventually we're going to start looking at various types of coordinate systems. And coordinate systems are independent of absolute values. So we're going to get different values for, say, a rectangular coordinate, cylindrical coordinate, and t, but that the absolute quantities are invariant. They always stay the same. So I throw this up because this is the projectile motion absolute or constant acceleration case, and these are the equations we derived in the previous lecture. V equals ds dt, acceleration dv dt, acceleration equals v dv ds. And you can also say V is equal to V naught plus ACT, S is equals S naught plus V naught T, 1/2 ACT squared, V squared equals V naught squared plus twice AC, S minus S naught. So S minus S naught, recall, is distance traveled. These are all standard equations, and you already have seen them, but let's apply them for the projectile motion and a constant acceleration of c. And we're going to use Cartesian coordinates here. And the only other thing, I'd just remind you how we got that third equation at the top. Acceleration equals v dv ds. So this is not a very well-drawn parabola, but it's supposed to be a parabola. But I have velocity at the top or at the bottom here, which is the initial velocity of the particle, and that particle is going to have v naught at some theta. And if I split it up into parts, I can say that's v naught x and v naught y, and those are standard values that I'll continue throughout, that I'll use in my equations. And you can expect that because I'm going to break it up into component parts. I'll look at the x and y, or the horizontal and vertical components, separately. So if I look at the particle, it's got a gravitational acceleration, which is g, which is acting downward, and it'll have vx, vy that will be different than v naught x, v naught y. Vx at the very top is going to be completely horizontal. It'll be parallel to the x-axis. There is no vy because the particle is not rising or falling yet, but it's at the top of its travel. G is the acceleration acting downward. When I get to the same corresponding point as I did over here, I'll have Vy, which is acting downward, and Vx, which is continuing to be the same absolute value. So it's a constant velocity in the horizontal direction. There is no acceleration in that direction, but there is an acceleration, or rather a deceleration, when you include g, and g is always downward at minus 9.81 meters per second squared. We write it differently, but we always include it in that direction. We have two equations that we can use for constant acceleration, and remember that two of the three are actually dependent on each other, and so it doesn't really work very well. In the horizontal direction, we really only have position. Velocity is equal to velocity x. Acceleration y equals minus g, and we have the horizontal motion and the vertical motion. So that's your total set of equations that you have. Vx equals v naught x equals x naught plus v naught xt for the horizontal, vy equals v naught y plus gt, or vy squared equals v naught squared y, 2gy minus y naught, and the second equation is y equals y naught plus v naught yt plus 1/2 gt squared. Projectile motion is really important to the course, and if you get a chance, and I know you're kind of overwhelmed with a lot of stuff, it's worth trying something called Tracker, where you can do projectile motion and sort of film it with your cameras. It works with a cell phone superbly, and see what's happening in these cases.